Hello again, welcome back. This exercise now we're going to look at using the hypergeometric probability distribution. If you've watched my previous videos, we just did some videos on the Poisson probability distribution, and I said this is going to be your least favorite formula to use up until that point. Now it gets a little bit worse. Now our formula, thankfully we have formulas, we don't have to derive everything from scratch. Our formula is going to look like this. Now I'm going to explain what all of this means just in 1 second. Now, this is where we're going to begin. I don't blame you if you decide to stop the video and give up now. It looks a little bit tedious, but we'll be okay. This hypergeometric probability distribution. This is very similar to the binomial probability distribution, where we are estimating the probability of X number of successes occurring. So in this notation here, it's going to be the same. X is number of successes. And so this is going to give us the probability of X successes occurring. Now, when we were looking at the binomial probability, this was like flipping a coin. Each event was entirely independent. So if I had a probability of heads, probability of tails would be 1 minus p. And if I received, if I flip a coin and I receive a head, the first toss, the second time I flip the coin, these probabilities don't change. The probabilities are exactly the same every time I flip a coin because they're entirely independent of each other. So that was our binomial distribution. This one now, the reason this one's a little bit more complex to calculate is because that independence no longer exists. So consider a deck of cards. If we have 52 cards, and we know that four of those cards are aces. So if I were to ask, what's the probability of drawing an ace out of this deck of cards, well, you'd be able to tell me the probability of an ace is going to be 4. There's 4 in there out of 52. So you could calculate this for me, and you'd certainly be correct. So let's say you draw a card, and that card is an ace. So you pull the card and you successfully draw a card. Okay, good. Now set that card aside. Now, what's the probability of drawing another ace? Well, it's not the same anymore. So if this is the probability of an ace for the first draw, the probability of an ace in the second draw, well, now there's only 3 left in the deck, and the deck only has 51 cards left in it. So the probability changes with each event. So this now is going to follow a hypergeometric probability distribution. Now, I'm going to do an easier example. Well, maybe easier, depending on how you see it. A little bit easier example first, and then we'll come back and we'll do another exercise using a deck of cards in exercise 5.7b. So for now, let's just look at this shipping company one. So we have a shipping company receives shipment of 15 items. A random sample of 6 is selected, and we reject this shipment if any of these items fail to meet minimum quality requirements. Okay, so what do we have? Let's look at, we have a population size of 15. So let me draw, where can I draw this? Let's draw this up here. Here's my population. Capital N is 15. So I'm going to use the same notation that I have over in the formula here. So N is population size. So that population is divided into those units that meet our quality specification and those units that fail to meet our quality specification. So I'm going to split it, not quite in half, it's quite arbitrary where I'm drawing that line, it doesn't matter. So here I'm going to draw, well, we have some number of failures and some number of successes. Now what we're doing here is we're trying to identify defective items. So I'm going to call R which is our success, number of successes, or number of events that we're identifying. In this case, this is going to be defective item. Oops. So number of defective items. So over here, this is going to be R is my number of defective items. And so over here, N minus R is my number of failures, or in this context of this case, the number of items that meet our quality specification. Okay, so I've divided that 15 into the successes and the failures, or in this case, I've divided the 15 into the defective and the non-defective. Now, from this population of 15, we take a sample. So we're going to take a sample. I'm going to draw a different color because this is going to change. I'm going to draw a sample. So let's say I take a sample and it's these items, whatever, the space is irrelevant. So I take a sample out of here. This is lowercase n, that's hard to see. This is lowercase n. My sample size in this case is 6. So I take a sample of 6 out of there. Now, of those, I want to identify what proportion of those are going to be failures, or in this case, we'll call those a success from the sample. So that's our x that I've already defined here. So here's our x. Those are our successes, or in this case, the defective items within the sample. And this is going to be n minus x. So here I'm defining across this red line. So within that sample, some of those items are defective and some of those items are success. So here the last one, this is my sample size. Okay, so we have n, our population, is divided into successes and failures. And then we have our sample size, and this is divided into successes and failures. Okay, so there's the notation that we're going to be using. These are success, either in the population or in the sample, and these are failures, either in the population or in the sample. Okay, so we've got this divided up. So what we have here in the formula, now all of these terms ought to make sense. So hopefully they'll start to make sense. So here, this is the number of successes in the population, number of successes in the sample, and here's failures in the population, failures in the sample. Here's the size of the population, here's the size of the sample. Okay, now we've got all of that figured out. Now let's plug in our numbers that correspond with the first problem in part A. So we already have, oops, let me clear some space in here. My eraser's dead, there we go. Okay. Draw this line back in. So we have 15 population, our sample size is 6. Now, my first one, of course my eraser is going to stop working. There we go. My first one, what is the probability of accepting a shipment with five defective items? Okay, so how can we look at this? If I have my shipment, I have population, and that shipment is 15. If there's 5 defective items, what this means is that R is equal to 15. So N minus R, sorry, what a silly mistake. So R is equal to 5. This is 5. So N minus R is equal to 10. Those are our number of good items, and there's 5 defective items. And I'm taking a sample. We're going to reject it if any item fails to meet these quality specifications. And what the problem is asking us, what's the probability of accepting So what that means is, what's the probability then of taking a sample that has no defective items in it? So what this means is x is equal to 0, n minus x is equal to 6. So from this population of 15 that contains 10 good items, 5 bad items, if I take a sample of size 6, what's the probability that that sample of size 6 contains no defective items, which will lead me to accept it? If it contains any, right, if any contained a defective item, I'm going to reject it. So what's the probability of accepting a shipment that contains 5 defective items? Okay, so now we can put these numbers into this formula. So f of 0, because this sample doesn't contain any defective items, otherwise I would reject it. So the probability of accepting it, I'm repeating myself a lot, right? The probability of accepting it means that that sample contains all good items in it, so 0 defective items. And now we can plug in our values. So this is going to be 5, and x is 0. And over here, this is going to be 10, and this is n minus x is 6, divided by our population, 15, sample is 6. Now, of course, you know that this notation is shorthand for calculating these combinations. So this becomes f of 0, this is 5 factorial, divided by 0 factorial times 5 factorial. This is 10 factorial divided by 6 factorial times 4 factorial divided by 15 factorial divided by, here I have 6 factorial, and 15 minus 6 is 9 factorial. Okay, so a little bit tedious to calculate. Let's get started. So the first one, actually the first fraction here, this one, 0 factorial is equal to 1. 5 factorial over 5 factorial, that's also going to be equal to 1. So we don't really need to calculate that one again. So that value is just going to be 1. So now the next one, this is, let me move this over here. So this is going to be 10 factorial divided by, I'm going to open brackets, 6 factorial times 4 factorial, close brackets, that equals 210. So there's 1 times 210, there's my numerator. The denominator now, 15 factorial divided by 6 factorial times 9 factorial equals 5005. And so my final answer will be 210 divided by 5005, and there's our probability, 0.042. 0.042. So there we have it, the probability of accepting a shipment that contains 5 defective items. So if I have 15 items in that shipment, 5 of them are defective. The probability that I will take a sample of 6 that contain no defective items, so that I would accept, the probability that it contains no defective items leading me to accept is 0.042. Okay, I hope that makes a little bit of sense. Let's go on now to part B. What's the probability of accepting a shipment with 1 defective item? So here I'm going to clean up some space. Oops, I didn't mean to erase my diagram there. Let's start over from here. Okay. So now we're going to change some of these values. So I have, let's see, it still contains 5. I didn't need to erase this, so we still have a sample of 15. Contains 5 defective items. What's the probability of accepting a shipment that contains 5 defective items? Oh, okay, I made a silly little mistake. So now it's not 5 anymore. Now that shipment contains only 1 defective item. So now we're looking here. The 1 defective item, r is equal to 1. So n minus r is equal to 14. So now again, I take a sample of size 6, and I'm going to accept it. I'm going to accept it, which means that x is equal to 0. There's no defective items in this sample, and so n minus x is equal to 6. This is still a sample of size 6. So we go through the same calculation again. F of 0. Now this changes to 1 and 0. This is 15 minus, let me just put in the numbers. This is 14. 15 minus 1. N minus x is 6. And this is 15 over 6 again in our denominator. Okay. And now let's expand this. So 1 factorial over 0 and 1. So that value doesn't change. This is 14 factorial over 6 factorial, and 14 minus 6 is 8 factorial, divided by 15 factorial. 6 and 15 minus 6 is 9 factorial. Good. Again, so this first term is going to be equal to 1. The second term, I will calculate this one. 14 factorial divided by 6 factorial times 8 factorial. So that's 3003. And in our denominator, this hasn't really changed from the first problem. 15 factorial divided by 6 factorial times, oops. Try that again. 15 factorial divided by 6 factorial times 9, 5005. So now 3003 divided by 5005.6, 0.6 would be our probability of accepting a shipment that has 1 defective item in it. Okay, we're getting there. Last one. What is the probability of rejecting a shipment with 1 defective item in it? Okay, now let's get rid of some of this. So now we're going to reject that shipment, which means, so the blue text, this stays the same. I still have my sample, my population is still 15. That shipment here, it says it contains 1 defective item, so r is still equal to 1, n minus r is still 14. But now, if I'm going to reject this shipment, it means that there's 1 defective item in that population. I draw a sample of 6. What's the probability that that sample of 6 contains that 1? That 1 defective. So here I have now this sample. This is that 1. This is x equals 1. And this is n minus x. N is still 6. So n minus x is equal to 5. So I have, again, 15 in that population. 1 of them is defective, 14 of them are good. I take a sample of 6. What's the probability that that sample of 6 contains 1 defective item? So that leads me to reject. Okay, now what we need to do is calculate probability of getting that 1. this is going to be 1 factorial. Let's just write it out here. 1 and 1. This is going to be 14 and 5. This is going to be 15 and 6. So 1 factorial over 1 factorial 0 factorial times 14 factorial over 5 factorial times 9 factorial divided by 15 factorial, and this part doesn't change, 6 factorial and 9 factorial. So again, this piece here is going to be 1. Now I have 14 factorial divided by 5 factorial times 9 factorial, 2002, divided by, this piece hasn't changed, let's calculate it just to be safe, 15 factorial divided by 6 factorial times 9 factorial, 5005. And so we have a final answer of 2002 divided by 5005, 0.4. 0.4. Wow. There we have it. We have all of our probabilities looking at this hypergeometric probability distribution, meaning that our events are no longer independent of one another. Once I've received one sample or one observation, one event has occurred, it impacts the probability of other events occurring. I hope this was helpful. It was long, past 20 minutes. That's longer than I ever want to be. I hope you got through this okay. If you did, thank you very much for watching. I hope it was helpful. Bye-bye.